All right, so we are going to talk about an introduction to applied cryptanalysis. So I will try to explain how in practice cryptanalysis works and why we do it. Okay, so let's start with some basic terminology. So you hear words like cryptology and cryptography, and with this course cryptanalysis. So let's give a very basic definitions, because actually in order to explain these terms or area of science, we have to use a few paragraphs to explain them, but I will try to give a very short definition. So cryptology is about secure communication in an insecure channel. So in cryptography, our aim is to, provide confidentiality, but also integrity, authentication, and so on. So encryption is just one part of cryptography, okay? So there are other areas. As you notice, I use the word cryptography and cryptology as if they are the same things. And at the end, they will be the same. So let me give the definitions of cryptography and cryptanalysis. Cryptography is about designing secure cryptosystems. Cryptanalysis is about analyzing or breaking cryptosystems. So you can assume that cryptology is the name of the general area, and cryptography and cryptanalysis are two parts of it. But nowadays, the words cryptology and cryptography are used interchangeably in every language, actually. So when I say cryptology or cryptography, I mean the same thing. So the course name is Applied Cryptanalysis, or my previous course was called Applied Cryptology, but we could easily change it to Applied Cryptography. Okay, so these are the basic definitions, but of course, these are very huge areas, and there are many sub-branches of cryptology. And cryptanalysis is just one of them. So cryptography solves a lot of security problems. So nowadays, most of our security solutions are at the bottom based on cryptographic solutions. So one of the solutions we solve is privacy of stored data, messages, and conversations. So this is important. We don't have to communicate all the time. For instance, think about your files in your hard drive in your computers. So they are stored data. So we call them data at rest. So if your laptop is stolen, then your privacy is lost, because the person who gets the hard drive also captures your files. So in order to avoid it, we can use encryption. So this way we provide privacy of stored data, messages, and conversations. But next thing is that maybe the data is not at rest, but it is in transit. Maybe I'm communicating with somebody, maybe I'm sending a file, but also maybe I'm calling somebody, sending an SMS or WhatsApp message or WhatsApp video call, and so on and so forth. So currently this Zoom session is another example. We are communicating. So there is a data in transit, but currently my voice and video is sent to you using the advanced encryption standard Cipher with a secret key of 256 bits. So we also solve the privacy of data in transit. But before moving on, maybe I should also say we actually solve another problem. We also provide the privacy of data in process. Think about it in this way. We are using cloud services in many times. So if you keep a file in the cloud and want to work on it, then you cannot keep it encrypted, right? Because you want the cloud to perform operations on the data. So the service provider should be able to see the data and do computations on it. But thanks to homomorphic encryption, we can avoid this problem. We can keep the data encrypted and tell the cloud service provider to perform operations on them. And at the end, when they did that operations on the encrypted data, the result will be as we wanted. So actually, cryptography solves this privacy or confidentiality problem in three cases: where data is at rest, in transit, and in process. We also solve the integrity of these cases. We can provide the integrity for any data in transit or at rest. It doesn't matter. So this way, we know that the data hasn't been modified or changed during the transmission or during the storage. Another problem that's solved by cryptography is user and data authentication. So for the integrity, let me go back. We can use hash functions, message authentication codes, authenticated encryption. For user and data authentication, we can use digital signatures. For data, we can also use authenticated encryption. Finally, we solve the transaction non-repudiation. So this can also be done by digital signatures, which we use a lot these days. Okay, so let's continue with more definitions. So here we are going to talk about a cryptosystem or a cipher. So the basic question is, what is a cryptosystem? So cryptosystem actually takes the plaintext and converts it to ciphertext. And the ciphertext can also be, again, by this cryptosystem transferred back to plaintext. So we use the word cipher or the cryptosystem. I prefer the word cipher. And the plaintext is what you want to protect. So this can be a file on your computer. It can be a WhatsApp message. It can be this video communication. So it is the plaintext. A cryptosystem is a pair of algorithms that convert plaintext to ciphertext and back. So ciphertext is the encrypted version of the plaintext, and ciphertext should appear like a random sequence. So we don't trust the communication channel because it can be listened, and we assume that the channel is always listened by some people. So instead of sending our message as a clear text, so we actually perform the encryption operation, convert it into ciphertext, but the ciphertext looks like a random sequence. So we send it through the insecure channel. Anybody seeing this message would not understand anything because it would look like a random sequence. But the person you want to communicate can decrypt it back and obtain your message. That is the basic idea behind the cipher. So let's look at the historical examples where we use pen and paper methods. You can do very simple stuff like scissor cipher and so on. I'm not going to that much detail, but let's look at a very nice example of an encryption. And this is actually used for a very long time. So it is called simple monoalphabetic substitution. In this scenario, in the cipher or cryptosystem, every letter is replaced by a letter. So here's an example. Write your alphabet. In this case, I wrote the English alphabet. So you write the alphabet again, but in an order that you prefer. So you actually permit the letters, okay? And this time, for this choice of yours, it is a secret key, okay? So when you write a text as a plain text, you turn it to ciphertext by replacing every A with key, every B with U, every C with E, and so on. And this is the ciphertext. You send it to the person you want to communicate. So they receive the message, and since they are going to have the same secret key, they will take the ciphertext and they will replace every K with A, every U with B, and so on. So very nice method. And it is hard to guess the secret key because there are many secret keys. So if you want to answer the question, how many different secret keys exist? English alphabet has 26 letters. So think about it in this way. You write the alphabet. So now you have to write a letter here. So you have 26 options. You write one of them, you're left with 25 options, 24, 23, and so on. So this is the number of possibilities are the multiplication of 26 times 25, 24, and so on, which is actually 26 factorial, and it is as large as this number. So there are many, many possibilities. So randomly guessing your secret key is hard, and you cannot try every secret key one by one. Even this was a pen and paper method. This number is really huge, and you cannot use today's computers to try all of them. So as you can see, we have a very nice encryption algorithm. So before talking about what is wrong with it, this is how a ciphertext looks like. So you write the plain text, replace the letters with respect to your secret key, and you also remove the blanks between words, and you also remove the punctuation mark. So this way, the result looks something really random, right? So this is the thing that you now want to decrypt or capture the secret key and so on. Since this course is about cryptanalysis, and most of the time we are going to perform statistical techniques, most of the cryptanalysis methods are actually statistical attacks. So here we are starting with the basic but the most important one. We started with simple monoalphabetic substitution, and I will show you how we can break it. Okay, so here the weakness is coming from the redundancy in the language. So what do we mean by that? For instance, think about English text. If you look at the words written in English, you will realize that the letter E appears more frequently than the others. Okay, this changes from language to language. For instance, in Turkish, A appears the most, and so on. So there is a redundancy in the language. So we can use this information to break the cipher, and this technique is called frequency analysis. So let's see how it can be done. So assume that you have a very long ciphertext like here, and you want to capture the plaintext. So frequency analysis is introduced by Al-Kindi in a manuscript deciphering cryptographic messages in 9th century. So as far as I know, this is the first cryptanalysis book that we have. If there were others, they are lost in time. And actually, a copy of this book is available in Topkapı Museum. So you can go there, and if you pay some money, you can take the photocopy of pages of this book. So as you can see, it is broken. This method is introduced in the 9th century, but the ideas applied here actually also applies the modern cryptanalysis techniques because it is a statistical attack, so we should understand how this works. So, as we said, it is based on the redundancy of the language. What you do is as follows. For a given language, find the long text and count the number of frequencies of every letter. So, take an English book, take a Turkish book, count how many times the letter A appears, B appears, and so on. So you are not interested in capital or lower letters, you are only interested in letters. Of course, doing this by hand will take a lot of time, but I think a simple code will do it in less than a second. For instance, in English, E is the letter that appears the most, the second place belongs to T, and so on. And in Turkish, the letter that appears the most is A. I think then it is E, and so on. So if the ciphertext is long enough, and we are assuming that it is written in English, the letter that appears the most in the ciphertext is most probably corresponds to E in the plaintext. So this is the idea. Let's go back to our secret key. So in your messages, you are replacing every E with Q. But if it is written in English, E should be the most appearing letter in your plaintext. So then Q should be the most appearing letter in your ciphertext. So the attacker captures the ciphertext here, counts the frequencies of every letter. So we count how many times a letter appears. The letter that appears the most, in this example Q, should belong to E. And similarly, the letter that appears the second most should belong to T, and so on. This way, you can actually capture all of them. But of course, this doesn't work all the time, because maybe the text is in a specific area. So instead of E, maybe A appears the most, and so on. So you have to do some trial and error techniques here, because there are a few reasons why the frequencies of the letters that you calculated from a very long book does not match with the frequencies of a ciphertext like here you captured. Okay, but this is how you break a very nice crypto system. All right. So in the symmetric crypto systems, we have a secret key, and we share the secret key with the persons that you want to communicate. And we are using this key for encryption and decryption. Maybe you can do a small modification, but this secret information is enough to perform encryption and decryption. So this actually introduces another problem, key distribution. In this scenario, you have to find a secure way of transmitting the secret key before you are communicating. In the past, we had to do it physically, put it in a locked briefcase and send it with agents and so on. But nowadays we have asymmetric key crypto systems where we have algorithms like Diffie-Hellman key exchange, where you can exchange a secret key through an insecure channel, or you can use RSA and so on to change secret keys. All right, so the secret key actually is used for encryption and decryption. In the previous scenario, you recall that I said that for this example there are this many secret keys. So this actually gives you a security upper bound, because if I have enough computational power, I can try each key one by one. So I try to decrypt this text, which every key, and check if it turns into something meaningful, right? So the length of your secret key actually determines your security upper bound. In modern algorithms, we of course use bits, so our secret key will be like 128 bits or 256 bits. So the question is, what should be the key size? An attacker that captures a single ciphertext can try to decrypt it with every possible key to check if it provides a meaningful plaintext. Such an attack is called an exhaustive search or brute force attack. Exhaustive search is a generic attack. In other words, it is valid for every cipher. It doesn't matter how complicated you design the cipher or not. Since you are using a secret key, an attacker can try everything one by one. So for a keyed cipher, the attacker is required to perform at most 2 to the k encryptions or decryptions, depending on how you're attacking. Thus, security of a symmetric encryption algorithm or a block cipher is upper bounded by exhaustive search, in other words, 2 to the k encryptions. This quantity is referred to as time complexity. So you can break every symmetric encryption algorithm with 2 to the k encryptions. So in this course, our aim is to find a non-generic attack that can break the same cipher, but with less than 2 to the k encryptions. So our time complexity should be less than this value in order for it to make sense. Yes, this also explains the same thing. Aim of the cryptanalyst: try to break the cipher, or it is run with this version with a time complexity less than 2 to the k encryptions, because we can always break it with 2 to the k encryptions. So how are these the exhaustive search attack? Nowadays we have many encryption algorithms. Very old one was called DES, probably you heard of it, and it used 56-bit secret key. So in order to break it, you have to perform 2 to the 56 encryptions. So years ago, and 2 to the 56 is this number, and years ago the computational power was not that good in the world, so it was hard to perform a brute force attack, except for most probably the agencies who had supercomputers. But nowadays, this many operations is not hard, even for a regular user. I mean, your laptop cannot perform this many operations in a second. But if you have a few GPUs, you can break this in a few months. So we have some algorithms that use 80-bit secret key. So 2 to the 8 is this. Again, nowadays we don't accept 80-bit security, because we believe that it is not that hard to perform this many operations if you have enough computational power. So this is the minimum we suggest is 128. So it's a very huge number, as you can see. And currently, if you use every device in the world that can perform computations, regardless of CPU, GPU, FPGAs, ASICs, we cannot perform this many operations in a meaningful time. You have to maybe need billions of years. However, we can also increase the secret key larger. So for instance, advanced encryption standard supports 128-bit, 192-bit, and 256-bit keys. This is, we refer to as military grade security, because it doesn't matter if your data is secure today. We also want it to be secure maybe 200 years later. This is why you might want to stay on the safe side and use a larger key. So this number is really huge. Actually, it is closer. It is almost equivalent to number of atoms in the galaxy that is we can observe actually. So it's a very, very huge number. So this is important because if our computational power increases so much that we can break this, we can perform this many operations in a single second, you will not be able to break this anyway, because performing this many operations in a second means that you can actually do 2 to the 150 operations in a year. So you will need 2 to the 40 years, which is a very huge number. Okay. So as you can see, if we keep the secret key large enough, brute force attacks will not work. So this is why you need non-generic attacks. So you need to find the weakness in the cipher, and most of the time we are trying to find a statistical weakness so that we can exploit it and break the system. So in order to break a crypto system, a cryptanalysis may need different types of data. So if you only collect ciphertext, and we always assume that the attacker listens to the communication channel, so they always have every ciphertext available. So with only the ciphertext, you can break the crypto system. We call it a ciphertext only attack. So if you can break it only by knowing some plaintext and corresponding ciphertext, then we call it a non-plaintext attack. So if you can break a cipher, but if your attack works only some specific chosen in a plaintext chosen in a specific way, then we call it a chosen plaintext attack. And another attack scenario is as follows. So you choose the types of plaintext you need. So you capture them, you perform some operations, but depending on your results of your operation, now you ask again for plaintext, but the choice now depends on your calculation results. So this is called adaptively chosen plaintext. So as you can see, collecting data becomes harder as we move down the list. But they are still in scenarios they are meaningful, because sometimes you can capture the device. So you can have a free access by giving input and obtaining the output. So in those kind of scenarios, you can perform all of these attacks, of course, if there is a weakness in the cipher. So another thing is that the cryptanalysis needs is resources. So the success of an attack is measured according to the resources it uses, the time or effort required to perform the attack. So if it is a very fast attack, we generally give it in like seconds or minutes that it takes on a specific CPU or so on. But if it is a theoretical attack, generally we measure the time complexity in terms of encryption operations. So we can say that these attacks work if we can do 2 to the 100 encryptions and so on. Another resource we need is memory, the amount of memory or storage required to perform the attack. Since we are going to perform a lot of operations on the data, we have to store them. So this actually determines our memory. And finally, as we mentioned in the previous slides, we need to capture some ciphertext or plaintext and so on. So the amount of data required to perform the attack is actually called data, and its amount determines your data complexity. So by data, we mean the plaintext and ciphertext pairs that we need to capture to perform the attack. And finally, let's finish with this. So there are many cryptanalysis techniques, and we are actually discovering new techniques, FE ones, every year. So the differential cryptanalysis is one of the first and famous ones. It's introduced academically by Biham and Shamir in the 1980s, but we know that secret agencies knew it since the Second World War. Some Japanese documents shows that Japanese knew this technique since the Second World War. But this technique received many different variations in the years, and people keep discovering new techniques. Linear cryptanalysis is another major cryptanalysis technique introduced by Matsui in 1992. There are also different variations like multiple linear or multidimensional linear cryptanalysis. But there are also attacks that are completely unrelated to them, like slide attacks, integral cryptanalysis, invariant subspace attacks recently, and subspace trail attacks. These are the recently discovered. I mean, I'm saying recently, but they're 5 or 10 years old. But still, you don't discover a cryptanalysis technique that frequently. So We are going to talk about all of them actually, but our aim will be actually the differential cryptanalysis. Once we understand it, the rest will be more meaningful to us. So in the differential cryptanalysis, our aim is to change the input slightly, so maybe flip a single bit, and try to anticipate its effect on the output. So we are trying to, modify the plaintext and look at the changes in the ciphertext, and from this we will try to capture the secret key.